So hello everyone. Let us start from the eccentrically loaded column. As we know that the Euler's buckling load P. Okay, let me change the color. So as we know that Euler's buckling load is equals to pi square EI upon L effective square, and we know the values of L effective, that is the effective length where the bending moment is equals to 0, means the distance between the points where the bending moment is equals to 0. So that distance is L effective, and we know for the various columns what will be the value of L effective. So we are not bothered about this. We are now watching, or we are now going to learn the eccentrically loaded column. So in the Euler's buckling load, we know if this is the column, so the load buckling load P is passing through the axis of passing through the axis of the column. Right? Okay. So it is passing through the axis of the column. Now the scene is changed. Now the scene is changed where E is called as the elasticity constant and I is the minimum moment of inertia. Minimum moment of inertia means if this is the cross section of the column, this is x axis and this is y axis. So if this is B and this is D, and I am interested to find the moment of inertia about x-axis. So that will be b d cube by 12, and moment of inertia about y-axis is b cube d by 12, means db cube by 12. Okay, so the column will buckle about that axis of which the moment of inertia is minimum. So if the b is greater than d, okay, then we know this term rather than this term, means this is ixx, this term will be greater than this term. So what will we select? We select this, okay, for the calculation, because this is I minimum. So column will buckle about that x axis, means along y direction but x axis, about x axis, and buckle about y axis. Okay, so that we have seen. So now we are going to see the eccentrically loaded columns. So what do we mean by eccentrically loaded columns? So eccentrically loaded columns have two approaches. First one is the uniaxial eccentricity, and second one is the biaxial eccentricity. Okay, uniaxial eccentricity and the biaxial eccentricity. Okay, so what do you mean by the uniaxial eccentricity? Uniaxial eccentricity means if you have the column like this is the three-dimensional view of the column, and this is your, okay, I should drop properly. Okay, if this is your x-axis and this is your y-axis, this is x-axis and this is y-axis. Okay, and this is the point. Okay, this is the axis of the column, and we know the Euler's buckling load, the assumption for Euler's theory, that is column, the load should be passing through the axis of the column. Now we are changing the scenario. We are passing the load from here, having the distance from that axis of the column is ex. So ex is the eccentricity. So about ex, means by ex eccentricity we have applied the same load P. So its cross section would be like this. So this is x axis, this is y axis, and we have applied P load over here having the eccentricity ex. Okay, having the eccentricity ex, and we know this is the B and this is D. Okay, now we know in the columns always compressive load are being delivered on it. Okay, means in the column the compressive stresses are being developed, because column is not used for the tensile purpose, it is used for the compressive loads. Okay, compressive loads are subjected on the columns, so compressive or normal as well as bending stresses will come. Okay, why? When that P is over that point or axis of the column, only the normal stresses are being come. Okay, but we have the eccentricity. So as due to the eccentricity, there will be the normal as well as the bending. Okay, normal as well as bending stresses are there. Okay, normal as well as bending stresses will be developed. Okay, if I shift P load to the center. Okay, from center to ex eccentricity. Now we know if I am interested to shift the P load from this eccentricity to the axis of the column itself, so force as well as movement comes into the picture. Okay, so force as well as movement comes into the picture, and we will analyze it separately and use the principle of superposition. Okay, so this is the column, this is the cross section of the column. We say if I am interested, let's see here, I am interested to deliver that P force over that axis, the moment also comes into the picture. Okay, the moment also comes into the picture. So let us say the P load is acting over here and the moment is acted over here. Okay, not like this, the moment will come like this, because the buckling would be, means bending would be on that side. Okay, bending would be on that side because of eccentricity on positive x-axis. This is x dash, this is y dash. Okay, eccentricity about the x dash. So buckling will be about the x-axis, not about the y-axis, but along the x-axis. Okay, so uniform stresses are there due to the force. Okay, we know the stresses will come, and its stress diagram would be like this, and this would be like this. Okay, so due to the moment, bending stresses are there. Okay, we know the bending stresses distribution. Okay, so we know what we know, mi is equals to sigma y. Okay, so from that, bending moment is equals to, so sorry, bending moment into y, that is the maximum distance from the center, maximum distance of the fiber from the center upon moment of inertia is equals to sigma, and we are interested to nomenclate each as a bending stress. Okay, we are interested to nomenclate it as a bending stress. So bending stress would be my by I. So what will be the moment? Moment is nothing but force into perpendicular distance, that is eccentricity. Okay, p into ex. Okay, now the total stresses will become, okay, total stresses will become, we add the total stresses, we all add the total stresses, but always understand, I have already drawn here the diagram. This is the, as there is a compressive stresses, we have drawn this stress bending stress distribution, normal stress diagram as a negative sign, and this is the bending stress diagram. So this would be like this. So this is positive, this is negative, means the compression, the tension, and the tension over here, sorry, compression over here. So we know we have to have the compressive load on the column, means our column does not experience or shall not experience the tensile load. If it is experiencing the tensile load, then it is incorrect or undesirable. Okay, so for that we have three cases. What are they? We know sigma d be the direct stresses, that is force upon cross sectional area, and sigma b be the bending stresses, that is my by I. Okay, so this is a, this is b, so we will superimpose them. Okay, so we have two options. The first case would be like this: whenever our direct stress is greater than the bending stress, direct stress is greater than the bending stress, means there would have the compressibility in the picture. Okay, compressive stresses in that picture. Okay, so if now I have next step or next case, if there is, if there is direct stress is equals to the bending stress and direct stresses are equal, then there must be this kind of case. Okay, this kind of case, and having negative sign. And third case is our direct stress is less than bending stress. If direct stress is less than bending stress, means there would have the tension comes into the picture in overall. These are the overall diagrams, huh? It is just for understanding. So this is positive, this is negative, means this is undesirable. Why undesirable? Because in our column we are not interested to have the tensile stress. Okay, tension is not allowed in the column. Okay, compression is allowed, but we want pure compression. For that, our limiting case is sigma d should be equals to sigma b, that is direct stress should be equals to bending stress, or direct stress would be greater than bending stress, means our limiting case is this. And the case in which our column is experiencing the compressive load, compressive stresses, that is sigma d, direct or normal stress, direct means normal stress should be greater than or equals to the bending stress, should be greater than or equal to bending stress. Okay, so for no tension in the column, we have the case. Okay, for no tension in the column, we have the case that the stress at A shall not exceed the value 0, means it should not be positive. It should be 0. It may be 0, but it should not be positive. If it is a positive, then there would be the compression. So direct stress plus bending stress at that A should be equals to 0 for limiting case. Okay, for limiting case. So from that we can say our bending stress is equals to minus times direct stress. Okay, so for the limiting case, we have to only understand our sum of bending stress and the direct stress is equals to 0. And bending stress we know, as there is a direct stress is always minus p by a, because minus sign because of the compressive load, and bending stress is my by I. Okay, that is equals to 0. Okay, you can say it is less than or equal to 0. For the limiting case, we'll see later on. We'll see what should be our eccentricity for the column. So we can write minus p by a plus my by I is less than or equal to 0, and from that we can write our p and area is bd. Okay, p upon bd plus moment is what? P into ex into y should be y max by I is less than or equals to 0. Same case. So if we solve this all, y should be y max means from the neutral axis, what is the distance from the neutral axis? Let's see, what is the distance? The distance is b by 2. Okay, this distance is b by 2, maximum distance from the neutral axis. So for minus p upon b into d plus p into ex into y max is b by 2 upon I, that should be less than or equals to 0. Okay, if we cancel out this p, it could be cancelled out. So ex should be less than or equals to b by 6, that we should understand. Okay, means this is the derivation. This is not needed for us. Just needed is if we have the eccentrically loaded column, then like this, having eccentricity at ex distance. Let's say this is the ex distance and this is x axis, x dash, this is y dash, and eccentricity at this ex, this is b and this is d. So our ex should be less than or equals to b by 6, means this whole b, this is b, you can see width of the column, it is less than, means eccentricity should be less than or equal to b by 6. Similarly, eccentricity along the y direction should be less than or equals to d by 6. Okay, so we can use the similar case as well. Means ultimately, if this is the cross section of the column, if this is the cross section of the column and this is b and this is d, this is x dash, y dash, and this is our load is acting, and this is eccentricity. So for that, and if in the second case, I'm telling you, in the second case, if I have the eccentricity along y-axis ey, so always remember ex should be less than or equals to b by 6 and ey should be less than or equals to d by 6. It is called as the middle third rule. What? Middle third rule. Why middle third? Because if you see here, if I cut into two portions, means cut into three portions, so it is telling us that our load, if I cut this b in three portion and d in three portions, so it is saying that our load should not exceed from that area. Okay, means middle third means L third or B third or D third of the column about that particular direction, so that our column will not have the tensile stresses in the picture. Okay, and whatever the area in which we have to apply that force P, due to which our column will experience only compressive stresses, that area is called as the kern. Okay, this area is called as kern. Okay, kern of the column. This is kern of the column. This is like this. So let us have idea. This is b by 3 and this is d by 3. Let's have the idea of the kern. So kern is the region of the cross section through which load passes. There will not be any tension anywhere in the section. There will not be any tension anywhere in the section. So if our column is rectangular, okay, if our column having the rectangular section, our kern is always rhombus. Okay, for rectangular column, our kern is rhombus. For circular column, our kern is circle. For square column, this is rectangle. This is rectangle. For square column, this would be square. Kern would be square. For hollow circular column, our kern will be circle itself. And for I section, the kern would be a rhombus. Okay, for I section, kern would be rhombus. So for rectangle, rhombus, circle, rhombus, square, square, hollow circle, circle, and I section, rhombus again. This is the shape of the kern. Okay, this should be the shape of the kern. So I understood what is the eccentrically loaded column. What do we mean by the eccentrically loaded column? It tells us that what should what should be the eccentricity through which our column will experience the only compressive stresses, not the tensile stresses, and the area in which we have to apply the force, or we apply the force and only compressive stresses will become, that region is called as the kern. Okay, and for rectangle, kern is rhombus. For square, the kern is a square. For circle, kern is a circle. For hollow circle, kern is the circle, and for I section, kern is the rhombus again. So these is all about this. For uniaxial eccentricity, the most important thing that we should understand is that that these two diagrams, and our our direct stress should be greater than bending stress. Okay, greater than or equals to bending stress. I mean to say bending stress plus direct stress. We know direct stress has negative value, so bending stress plus direct stress should be less than or equals to 0. Okay, should be less than or equals to 0, and due to which we can prove it. We can prove it. Now, if we have the biaxial eccentricity, means I will draw the column over here. If this is the column, what do we mean by biaxial eccentricity? Biaxial eccentricity means we have eccentricity on both x and y direction, means there would have the 2D, or means there must have some x coordinate and y coordinate. Okay, it is like this. So let us see for the biaxial eccentricity. So for the biaxial eccentricity, we have the cross section like this. Let's say this is the rectangular cross section, and this is our x dash, this is y dash. What should be the buckling? Okay, we know buckling about that axis in which moment of inertia is minimum. Okay, about that axis means along another axis. Okay, so this is the axis of the column. This is the p load that is acting, having the eccentricity. This is ex and this is ey. Ex because along x-axis. This is distance from y-axis is x. Distance from x-axis is y. So ex and ey. So this is b and this is d. That we should understand. We can draw. Now we know there are the stresses which there are the stresses induced. These stresses are direct stresses as well as bending stresses. So direct stresses is minus p by a. Bending stresses, we cannot tell about the sign of bending stresses. Okay, so bending stresses would be, now let us see, as this is the biaxial eccentricity, bending stress formula is my by I. As it is the biaxial eccentricity, there would have compressive as well as, or compressive or the tensile stresses. There would have, okay, compressive or tensile stresses. It is depend on that particular point of the column. Okay, it depends on that particular point on the column on which we are interested to find the stress. Okay, you will get it if you see later on. So there would have bending stresses on both directions. So I will say it is equals to p into ex, means moment about y axis into the distance of axis, okay, upon I, plus p into ey upon I into the y. Then here is the question, what would be y? Okay, what is the value of y? So for that we are finding the biaxial eccentricity for such a point. Okay, let us say q point is there, and on that q point we are finding out the stresses. Okay, overall stress due to the bending as well as normal stress. Okay, so it is having the coordinate a comma b. Okay, suppose a comma b. Let's say a means distance from y axis, this is a, distance from x axis it is b. Okay, because coordinate. So distance from y axis is called as x and distance from x axis is called as y. Okay, and we are interested to find the stress at point q. So minus p by a plus minus, here is also plus minus, p into ex, that moment about y axis into distance from y axis. What is the distance from y axis? It is x upon the moment of inertia that is about y axis, that is y. And distance from x axis means this is the moment about x axis. You can see if the load is acting over here, the moment would be about, means moment must be about x axis. So this is the moment, but moment into y, what should be the value of y? We are interested to find the stress at point q. So y means distance from x axis, that would be b, and this is xx. Why xx? Because it is about the x axis. Okay, so this is in the biaxial eccentricity, means if we are interested to find the stress at q, we know direct stress plus bending stress is the overall stress. So that is equals to direct stress is compressive in nature, so plus minus p into ex. Okay, p into ex into x. Why p into ex into x? Because p into ex is nothing but the moment about y axis due to p force, into x means distance of that q point from the x axis upon iyy, plus minus p ey into b upon Ixx. Why PEY? This is the moment about x-axis, means it will try to rotate like this. Okay, it will try to rotate like this, and the point Q has the distance from y-axis is x. Or rather than writing x, not x, y. Ey into y upon Ixx. So that is the formula. Many students are reciting these formulas like sigma q is equals to minus p by a plus minus pex into x upon I by y plus minus pey y upon Ixx. So it is just understanding and imagination of the column, how the column will buckle and how the stresses are coming. So now let us see here, if you have this type of cross section, and this is the x dash, this is y dash. Okay, and you have biaxial eccentricity, means this is p load acting over here, and you have the eccentricity from x-axis is ex and eccentricity from y-axis ey. If your q point is over here, your q point is over here, due to the force p, this point as this a a point will have maximum compressive stresses. Why? Because due to this point p, column will buckle like this, buckle like this. Okay, column will buckle like this, and at point a there will be the maximum, there will be the maximum compressive stresses. Okay, maximum compressive stresses means in 3D the column will buckle like this. Due to that p force, column will buckle like this. So if the p is acting over here, this is the side where the compression comes, and this is the point a where the compression would be maximum. Okay, means buckling would be like this. Here will be tension, here will be compression. Okay, so that's all about the eccentricity, uniaxial and biaxial. Thank you.